Okay. So last time, this is wrong chapter. Last time in class, we did start hypothesis testing with the z-test. This is what we've been really working up to all semester long. We're going to do the z-test, which is what we started in this chapter. We're going to do the t-test, which is what we'll do in the next chapter or two. And we're also eventually going to get to the f-test. And those are the three big hypothesis tests we're going to learn: the z-test, the t-test, and the f-test. The z-test is what we're going to do more of today. Last time what we did was a two-tailed test. Let's see. So you can kind of, visualize a two-tailed test like this. Is probably not a bad way to do it. For a two-tailed test, you have this middle number right here. This represents like the null hypothesis. So if there's the null hypothesis, firstly, let's go to our last example. The example that we did last time was the null hypothesis is that the mean score on the math test when you're taking math drug was 80. And if you recall, the population mean for this example was 80 as well. So basically what the saying is, for people that take the math drug, their score on this math test is going to be the exact same as the population mean. There's no difference at all. That's the null hypothesis. The alternative hypothesis for this example was the mean of people that take the math drug is different than 80. And I mentioned last time that you could kind of decompose this research, this alternative hypothesis, into two components. Can someone remind me what are the two components that you can break down? This statement is mu does not equal 80. And there's basically two sides of this, two tails of this. What are the two components of the statement, mu does not equal 80? Does anyone remember from last time? Anyone remember what mu does not equal 80? You can basically break that statement down into two little pieces or two components. What are those two pieces?
Mu is greater than 80 and mu is less than 80.
Exactly. Mu is 80. Mu is greater than 80 would be consistent with this. So if you run the math test with people that take the drug and they score greater than 80, then that's consistent with the research hypothesis. Or alternatively, if you give people the math drug and it causes them to do way worse in the math test and they get like a 70 or 60 or something like that, then that would also be consistent with this research hypothesis, because all the research hypothesis is saying is people that take math drug, they're not going to score 80. It's either going to be higher than 80 or it's going to be lower than 80. That's an example of a two-tailed test because both sides of that inequality, the fact that the research hypothesis suggests that the math drug can either cause an increase in the scores or it can cause a decrease in the scores. And just to kind of remember, and so this is how you can kind of visualize that. If you run the data and you collect a sample mean and you find that sample mean lands anywhere in this white area right here, then you accept the null hypothesis. This blue area, if the sample mean that you calculate lands in this blue area, then you reject the null hypothesis. Does anyone remember what the name of this blue area is? There's a name for it. It starts with a C. Anyone remember?
Critical region.
Critical region is correct. The blue area is the critical region. If your sample mean lands there, then you reject the null hypothesis. Let's see here. What else? We're just reviewing some things, getting us warmed up. Alpha level. Anyone remember that in psychology, I mentioned last time that there's an alpha level which is used most commonly? Anyone remember what that alpha level is? %5 is that alpha level, or 0.05, which means that 5% of the area underneath the normal distribution lies in those two tails. So if our alpha level is 5%, that is 0.05, and we have a two-tailed test, please remember that what you do is you take those two tails and you divide the 5% evenly among them. So with a two-tailed test, with alpha equals 0.05, there's going to be 2.5% in one tail, and there's also going to be 2.5% in the other tail. So this is alpha equals 0.05, two tails. You're dividing that 5%. You're dividing that 0.05 into the two tails so that each tail gets half of the 5%. That is 2.5% in each tail. Here are some important numbers here. So this critical, these are the two critical Z's, which are very common. If you're doing a two-tailed test, plus or minus 1.96, a two-tailed test with alpha equals 0.05, then 1.96 is the critical Z, meaning if you calculate a sample mean and the Z-score that corresponds to that sample mean is either greater than 1.96 or less than negative 1.96. So if it's in one of those two tails, then you reject the null hypothesis. So for a two-tailed test, alpha equals 0.05, the critical Z is plus or minus 1.96. That is what marks the boundary into the critical region, is that Z-score of plus or minus 1.96. If we're doing a one-tailed test with alpha equals 0.05, things change. For a one-tailed test, there's only one side of the distribution, either the right side of the distribution or the left side of the distribution, where if the Z-score for the sample mean falls into one of those two tails, only one of those two tails actually results in you saying we have a significant difference. We should reject the null hypothesis. So, and I did mention this last time, when we have a one-tailed test with alpha equals 0.05, we only have one tail now. So all 5% of the critical region falls in that one tail. With a one-tailed test, you're no longer dividing 5% into two tails. You're putting 5% all into one tail. And so when you do that, the critical region is marked 1.65. That's assuming, by the way, that it's the right tail that you care about. If it's the left tail that you care about, it would be negative 1.65 that marks the critical region. So I have an example. That's what we're going to do today, and then we'll be done with chapter 7. I have an example of a one-tailed test that we will do. There's some more critical Z's. That's the work that we did from last time. So here's how to visualize that one-tailed test. So we have some experiment, and we predict that if the treatment has a significant effect, then what that treatment is going to do is and using our example from last time of the math test performance, the null hypothesis was doing math drug is not going to influence people's math performance. If you have a one-tailed test, then if the sample mean falls somewhere in this white section at all, even way over here, then you accept the null hypothesis. For a one-tailed test, you only are willing to reject the null hypothesis if the sample mean falls in one tail. And you can see that one tail over here would be over here on the blue side. So you would use this if you are really, really confident that the math drug could only improve performance on the test, that there's just no feasible way that math drug could cause people's performance to decrease on the test, then you basically ignore the possibility that math drug could reduce scores on the test, and you put all 5% into the one tail. All 5% of our alpha goes into one tail. And that's what's shown here. Even if you get a math drug test score that's way over here, you still accept the null hypothesis when you're using a one-tailed test, because you will only reject the null hypothesis when the sample mean falls into this critical region where there's only one tail. All 5% of the critical region is in one tail for a one-tailed test. So here is the one-tailed example that we're going to do for today. And this is taken from the book. So this is a good example of one-tailed test because it gives you, it was designed so that a one-tailed research hypothesis is what makes the most amount of sense. So this is taken from chapter 7. So our population mean here is the amount of calories that people consume for a trip to Starbucks, and the population is based on trips to Starbucks from all American cities. And so 247 calories was the average amount of calories consumed at Starbucks. This is the population mean. So it's taking many cities across the entire United States, we'll say. But we're interested, our sample mean, we're interested particularly about the amount of calories that are consumed at Starbucks visits to Starbucks stores in New York. And the reason theoretically we care about this is because in New York only, there's a law that requires the amount of calories for every item at Starbucks to be posted on the menu. All of the calories are posted on the menu in New York, but that's not the case at the other cities in America. So I don't know if that's actually true in real life, but let's assume that this is true. Only in New York are the calories posted for the amount of for items at Starbucks. And our sample size is 1,000. So we have 1,000 people that went to Starbucks in New York, and we averaged together the amount of calories that they consumed on their trip to Starbucks. So the sample size was 1,000 people. Our standard deviation was 201. And this is going to be a one-tailed test. And so the one-tailed test, once again, you could always tell whether it's a one-tailed test because by looking at the research hypothesis. So our research hypothesis here, and we'll go back to the null hypothesis in a second. Our research hypothesis is that the amount of calories consumed by people in New York Starbucks will be less than 247. And if you think about it, this makes sense. Only New York Starbucks have calories written on the menu. And the idea here is that if people are ordering at a restaurant and they can see the amount of calories that they're about to eat, then that increases the likelihood that they will buy something which is leaner, that will have less calories. When you're aware of the amount of calories that you're eating, then in theory, that should decrease the amount of calories that you are going to purchase, the amount of calories that you are about to consume. And it shouldn't increase it. Like we won't even really, for a one-tailed test, in this particular one-tailed test, we won't even consider the possibility that if the calories are posted on the menu, that would cause people to eat more calories. That just seems silly. Why would that be the case? So we're going to assume that there's only one, the research hypothesis is one directional, that it's going to cause, if there's a significant effect of having the calories posted on the menu, that effect will be to reduce the amount of calories people consume. There's no reason to believe that it could possibly increase the amount of calories to consume. So our research hypothesis is mu, the amount of calories consumed by people in New York, will be less than 247. You can tell that this is a one-tailed test because there's only one half of the there's only one inequality. For the other research hypothesis that we just talked about, there was a mu as less than something, and there was also a mu as greater than something. But for this one, there's only the mu as less than something, and so that's how you can tell that this is a one-tailed test. The null hypothesis then is any other possibility. So this null hypothesis includes kind of two possibilities. That is, mu is equal to 247. That would be considered a null effect. That means if we find that mu equals around 247, that people in New York, they consume 247 calories. That means that having the amount of calories written on the menu has no effect on people's consuming the amount of calories they eat. Similarly, if it turns out that the amount of calories written on the menu increases the amount of calories that people consume, that's going to count as a null effect. We're going to account that. We will count that as being a null effect, that there is no significant effect of the treatment. And this is, once again, because our research hypothesis only has one tail. We believe so strongly that the only possible effect of having the calories posted on the menu would be to reduce the amount of calories that people consume, that will basically say will count as our null hypothesis if the amount of calories consumed by people in New York equals 247, or if it's greater than 247, we'll say that means there's no treatment effect. And the only treatment effect that we'll consider significant will be if the amount of calories is significantly reduced. So we'll be doing a one-tailed test with alpha equals 0.05, which means that we will be using the critical Z of negative 1.65. So what we'll be doing here is we'll be calculating a sample mean for, we'll be calculating a Z-score for the sample mean of 232. And if this score falls into the critical region, that is, if the Z-score that corresponds to 232 is less than Z equals negative 1.65, then we're going to reject the null hypothesis. I'll say that again. Actually, no, I think I have a picture. So we'll just, here is my beautiful artwork of kind of drawing this distribution and the critical region. So this would be like the population mean right here. It has a Z-score of 0 right here. And then our critical Z is right here. Z equals negative 1.65. What we're going to do once again is calculate a Z-score for our sample mean. I believe it was 232. 200, yeah, we're going to calculate a Z-score for our sample mean, and we're going to see where along this distribution does it fall. If our Z-score that corresponds to the sample mean of 232 falls anywhere in this white region right here, which is not shaded, then we accept the null hypothesis, even if it's way over here, because we only count one tail as being significant. Only one tail counts as the critical region. So if our Z-score for the sample mean falls anywhere in this white region, then we're going to say there's not a significant effect. If our Z-score falls in this critical region, that is, if our Z-score for the sample mean falls to the left of negative 1.65, that is, if our Z-score is less than negative 1.65, then we will count as this is a significant effect. That is, we'll say that having the calories posted in the Starbucks significantly reduces the amount of calories that people consume. So now what we need to do, this is our alpha is 5%, meaning that all 5% of the area in the critical region is right here in this one tail. So now what we need to do is calculate our Z statistic for the sample mean. So we're going to be using this formula right here, the one that we've now, this is the more advanced formula. This is the standard error right here. Just to remind you, this thing in the denominator is the standard error. And could someone remind me, what is the, how do we calculate, what is the formula for standard error? This symbol right here means standard error. How do we calculate the standard error? I'll give you a clue. It's something divided by something else. Could someone tell me what it is?
Is it the standard deviation divided by the square root of n?
Exactly. It is the standard deviation divided by the square root of n. And so if we went back to the couple slides ago, I already mentioned the population standard deviation is 201, which is right there. And the sample size, the amount of people that we took calories, we averaged their calories of people in New York was 1,000. So our standard error is 201 divided by the square root of 1,000. That's the denominator of our Z equation. This 232 right here, this is our sample mean. This is the amount of calories that people actually calculated when they went to Starbucks in New York. This 247 right here is the population mean. This is the amount of calories that people consumed at Starbucks across the nation at many various cities. So right here, even before I show that the answer is negative right here, it's a negative 2.36. But even before we calculated this Z-score, we should have known that our Z-score was going to be negative because our sample mean of 232 was less than our population mean of 247. And so we take this score of negative 2.36 and we put it and we post it along here. And if we were going to plot it, it would be somewhere about right here. You know, there's negative 1.65, this boundary right here, that's negative 1.65. We just got negative 2.36, which would be somewhere to the left, less than negative 1.65. Therefore, you can quite clearly see that the Z-score for our sample mean falls into this critical region. So we would reject the null hypothesis. That is, we would conclude that there is a significant effect. Having the calories posted on Starbucks in New York, people who see the calories in New York eat fewer calories on average than people across the whole population, which is all the cities in the United States where the calories are not posted. So that's it. Does anyone have a question? This was an example. We've now done an example with hypothesis test example. From last Wednesday, we did an example with two tails. This is an example where the hypothesis test has one tail. Does anyone have any questions or comments before we end chapter 7? All right, then let's move to chapter 8. And I do want to remind you, I'm switching slides. All these slides are available on Blackboard right now. They're Rosenthal chapter 7 slides, Rosenthal chapter 8 slides. Now we will get chapter 8 slides up. There they are. All right. So here's the chapter. Today, we're just going to be talking about these things called confidence intervals. Wednesday, the plan is to talk about effect size and statistical power. So here are the three topics once again: confidence intervals, effect size, and statistical power. Okay, so what are confidence intervals? Um, a confidence interval is a combination of two things. One is a point estimate, and the other is an interval estimate. A point estimate, basically, for us, is just the sample mean. We calculate some sample mean. And it's called a point estimate because it's basically a single number, and that single number represents the middle of a distribution. So we calculate our sample mean, and then we put that sample mean at the center of a distribution. And that's what it says here, a summary statistic. That's what the sample mean. It's just a single number. It's a single mean. And the usual lingo that people use for a confidence interval is that that sample mean is an estimate of the population mean, or is an estimate of the population parameter. The interval estimate, the more like common language that you might have actually heard even before you've taken a statistics class would be margin of error. So this is a term, margin of error is oftentimes used in like polling data, where you'll have, this is the mean score for this presidential candidate within a margin of error of so-and-so. The margin of error is basically like a little bit of numbers to the left and a little bit of numbers or an interval to the right of this sample mean. A famous example from psychology, for instance, would be Miller's famous number, the capacity of short-term memory, which the average capacity of short-term memory, according to old research by Miller, was 7 plus or minus 2. That plus or minus 2 would be the interval estimate for that Miller study. Basically, that means that the average short-term memory capacity of people is 7, but some people are about 2 higher than 7. So some people have short-term memories that are about 9. Some people have short-term memories that are less than 7, around 5. So 7 plus or minus 2. 7 would be the point estimate. That's a single number, which represents the population mean. And then the interval estimate would be the plus or minus 2. Some people score higher than 7 on their short-term memory ability. Some people score less than 7 on their short-term memory. And this is the crucial part of the confidence interval. So confidence interval, once again, is these two things. We're going to take the sample mean, we're going to put it in the center of a distribution, and then we're going to calculate an interval estimate, that is a margin of error, a confidence interval, and we're going to plot it on either side of the sample mean. So here's a couple things that, some things to remember about confidence intervals. So once again, I've mentioned this. The sample mean is the center of our distribution. We're basically a confidence interval. We're going to make a distribution. It's going to be a normal shaped distribution. The sample mean is going to be the center of this distribution. I really want to emphasize how this is different than what we've done before. In the very previous chapter, the thing that was at the center of the distributions was not the sample mean, it was the population mean. That is the crucial difference between what we're doing in this chapter compared to what we're doing in the last chapter. In chapter 7, the thing that was at the center of our distribution was the population mean. In this chapter, when we're making confidence intervals, the thing which is at the center of our distribution is the sample mean. And generally with confidence intervals, you're going to have a margin. The margin of error is going to be symmetrical. That is, there's going to be a margin of error, an interval estimate that goes to the left, and an interval estimate that goes to the right. And it forms this interval around our sample mean. This is, by the way, assuming a two-tailed test. If you have a one-tailed test, then in theory, what you should do with a confidence interval is you should actually only have your interval estimate be on one side of the sample mean or the other. However, for reasons that are not usually stated in any textbook, it is basically never occurs that people would make a one-tailed confidence interval. So we will only be focusing on two-tailed hypothesis or two-tailed confidence intervals in this chapter. So in this chapter, we're going to be focusing on 95% confidence intervals. And this 95% comes from the alpha that we usually choose in hypothesis test studies. So we already mentioned that the most common alpha in psychology is alpha equals 5%. Alpha equals 0.05. And this is taken, that 0.05 is taken from 100% minus 95% gives you 5%. So this is related to that alpha equals 5%, alpha equals 0.05. This is just like the inverse of that. So 95% confidence interval is what we're going to be focusing on this chapter. And this is the 95% confidence interval that we're making. It basically gives us the same information. Mathematically, it gives us the exact same information that we get from hypothesis tests in the last chapter. Basically, confidence intervals are another way of doing hypothesis tests. There really is. They're very mathematically, there is no difference. It says right here, there's no difference between confidence intervals and hypothesis tests. Basically, it's you use different computations, but the ultimate decision whether to accept or to reject the null hypothesis is the exact same whether you're using the hypothesis testing techniques that we learned in chapter 7 or whether you're using the confidence interval techniques that I'm going to show you in this chapter. There's really no mathematical difference. There's no important difference between confidence intervals and the hypothesis testing techniques that we learned in chapter 7. So let's see here. Here's the steps. I'll let you read those on your own. Well, no, I guess I'll talk about them really briefly. Draw a picture. I have that picture right there. So I'll draw a picture that's going to kind of give us an idea of what our confidence interval is going to look like. We need to have the bounds. So we'll have a left tail and a right tail of our confidence interval. We need to know the Z statistics that mark our boundaries, into the two tails. We're going to convert the C statistics into raw means. That's not going to mean a whole lot until I show you this picture in a second. And then this final step is just to make sure that the confidence interval that you calculated is reasonable, that you didn't make some error. So you should spend more time looking at these on your own. I just want to kind of go into the example right here. So first off, I'm going to show you, this is what the confidence interval that we're going to make looks like. So a confidence interval, it looks a lot like the hypothesis test stuff that we've been doing, except I want to remind you that when we're making a confidence interval, the thing which is in the center, this is not the population mean anymore. This is a sample mean. This is the sample mean. And I'm using, by the way, the exact same example that I used from the previous example. This is people score on the math test after taking math drug. Their average score was an 89. That was the sample mean. And now I'm plotting that in the center of a distribution. Please know that when we were doing hypothesis tests in chapter 7, the example we did that was just like this. The thing that was in the center of the distribution was the population mean. But when you're making a confidence interval, the thing which is at the center of the distribution is the sample mean. So the number 89 is in the center here. And then the boundaries are marked with Z equals negative 1.96, Z equals positive 1.96. The 95% confidence interval is the idea that this white space right here contains 95% of the area in the distribution. This white space is 95% of the distribution. And that means 2.5% is in this tail, 2.5% is in this tail. And this should look familiar. We've used this 1.9 plus or minus 1.96 before. This is the critical Z value that is used when alpha equals 0.05 for a two-tailed test. What do we get if we add up the percentage in the two tails right now? If we add up the amount of area in the left tail plus the amount of area in the right tail, what does that equal? Someone tell me.
5%.
5%. So that hasn't changed. They were using a 95% confidence interval, which means there's 95% in the middle, which means that there's 5. If you add together the area and the two tails, that's going to equal 5%. So this aspect is very, very similar to what we were doing in hypothesis testing in chapter 7. Really, the crucial difference now is what we consider the center of the distribution. The center of the distribution now is considered the sample mean, whereas in chapter 7, it was the population mean. So here is the exact example. So this is literally the exact same example that we did for chapter 7. We just talked about this at the beginning of class. We're going to now make a confidence interval for the same thing that we did the hypothesis test before. And we found, by the way, it was a significant difference. We found when we did the hypothesis test last time for this example, this is what we did Wednesday, we found that there was a significant difference. And it says right here in chapter 7, we rejected the null hypothesis because when we calculated the sample mean for our sample mean of 89, we calculated the Z-score for that. The Z-score was 2.25. The Z-score of 2.25 is greater than the critical Z of 1.96, which means that the Z-score that corresponds to the sample mean of 89 was in the critical region. Because it's in the critical region, we rejected the null hypothesis. We concluded that giving people math drug did have a significant influence on their math test performance. So our population mean, just to remind us of this example from Wednesday, was 80. That's the score of people on the math test who didn't take math drug. The standard deviation was 20. The question we asked was giving math drug, does it affect people's performance on the math test? Our sample size was 25. The sample mean was 89. So this is the score of people that took math drug. Standard error is this thing right here. This number 20 is the standard deviation divided by the square root of the sample size. So divided by the square root of 25, that gave us a standard error of 4. And once again, we rejected the null hypothesis because the z-score of 2.25 that we calculated was greater than the critical z of 1.96. Okay, so once again, we're going to be making this confidence interval right here. And really the main thing that we're doing when we're calculating a confidence interval is we have these numbers right here. This is our sample mean of 89. This is a z-score. Negative 1.96 is a z-score. Positive 1.96 is also a z-score. The basic math of a confidence interval is you are converting these two z-scores, these two critical z's, negative 1.96 and positive 1.96, you are converting those back into x values. And then you're making an interval of one x value on the left side of the sample mean to an x value on the right side. That's the interval. So these are z-scores right now, but basically we're going to use a pretty simple math computation to convert these two numbers back into x values. These are z values right now. We're going to use a basic math computation that's going to convert those numbers into x values, and then that will be the confidence interval. So it'll be an x value on the left side of our sample mean. That's one side of the interval, to the x value on the other side of our mean. That's the other side of the interval. And then the whole thing will be the 95% confidence interval. Here is the formula that we'll be using. I want to point out something that's very important, which is this formula looks a little bit different than what it would appear in your textbook, because the textbook does not write the word critical right there. But to me, that always confuses students. And so you need to remember that the z that you're using in this formula is the critical z. And so if we're doing alpha equals 0.05, and we're assuming a two-tailed test because that's what you always do for confidence intervals, the critical z is plus or minus 1.96. The book just says z right here, negative z and positive z, but that's confusing because when we're doing these hypothesis tests, we always have the z that corresponds to our sample mean, but we also have the critical z's, which marks the boundaries into the critical region. And when you're looking at the formulas in the book, it just says z, and so it's ambiguous in the book. Are they talking about the z that corresponds to the sample mean, or are they talking about the critical z's? And so it's really important to remember that when we're calculating a confidence interval, we will be using the critical z's. And so if we're doing a 95% confidence interval, which is what we'll be doing almost entirely in this chapter, this z will almost always be plus or minus 1.96. And that comes from the fact that when you're doing a two-tailed test with alpha equals 0.05, the critical z is plus or minus 1.96. So this is the lower interval. Up top, m lower means basically this is that number to the left of our sample mean in the distribution, and the m upper is the number which is to the right of our sample mean in that distribution I just showed you. So we're basically going to calculate two numbers. And the way you do that is you take the critical z, which in our case, it's negative 1.9. The negative critical z, which is on the left side of the distribution, will be negative 1.96. And you multiply it by this thing. What does the symbol mean? What does the symbol mean right here?
Standard error.
Thank you. It is standard error. Please note it's not standard deviation. You know that this is the standard error because it has this little sub m right here. This little sub m right here indicates that this is not the standard deviation. This is in fact the standard error. And we calculated this on the previous slide. We also calculated it way back in the day when we did Wednesday when we did this example. So negative 1.96 is our critical z times our standard error, which by the way, I'll go back to this. We calculated the standard error right here. It equals 4. And it's because the standard deviation of 20 divided by the square root of the sample size, 25, that equals 4. So and then you can see I plugged it in right here. And then the sample mean that we calculated, this is the score of people on the math test after they took math drug was 89. And so this is the lower bound of our confidence interval, the critical Z of negative 1.96 times the standard error, which is 4, plus our sample mean, 89. If you work all that out, you're going to get 81.16. So I want to reflect on what we just did. When we look at this thing right here is the Z-score. But when we're calculating a confidence interval, we want to know what is the X value which corresponds to the Z-score of negative 1.96. So we're converting in a confidence interval. This Z-score right here, negative 1.96, we are converting it to the actual X value that marks that boundary. And that's what this thing is right here. That negative 1.96 right here is the Z-score. We multiply times the standard error, add the sample mean, and this gives us the lower bound, 81.16. The upper bound is basically the exact same thing, except instead of using the negative critical Z, you use the positive critical Z. So instead of using negative 1.96, we now use positive 1.96 right here. 1.96 times, once again, the standard error of 4 plus 89. This gives us the upper bound, 96.84 is the upper bound. That is this number right here. This is a Z-score right here, 1.96. But when we're making a confidence interval, we're converting this Z-score into the X value that it represents. And that X value that is represented by the Z-score of 1.96 equals 96.84. So the book, in my opinion, makes confidence intervals way more complicated than they need to be. Really, all we're doing is we're converting the critical Z-score. You know, we have two of them, one on the left, one on the right. We're converting that critical Z-score into the X value that Z-score represents. The lower bound here is 81.16. The upper bound is 96.84. And so these two numbers are the confidence interval. And I mentioned at the beginning I'll show you how you would write the answer to a confidence interval here in a second. But I want to point out before we do that, I mentioned earlier that the confidence interval, it gives you the exact same decision whether to reject the null hypothesis or not. The technique is different. But if you do a confidence interval, it gives you literally the exact same information as to whether reject or accept the null hypothesis as you would get from doing the hypothesis testing technique that we did in chapter 7. The way you do the confidence interval, the method's slightly different. The question you ask is, does our population mean fall inside the confidence interval? If you recall, the mean score of people that did not take math drug was 80. And the question is, does this score of 80, does it fall within, is it inside the confidence interval? And the answer is no. 80 is outside. The confidence interval is everything which is between these two numbers. And you can see that 80 is not between these two numbers. Therefore, we reject the null hypothesis because 80 is not in the confidence interval. So as I said earlier, confidence intervals really are, they're kind of like the exact same thing as hypothesis testing, except the inverse. And that really is an accurate statement. We reject the null hypothesis because 80 is outside of this interval. So yeah, 80 does not fall in the confidence interval, therefore we reject the null hypothesis. And I mentioned, yeah, the confidence interval gives the exact same hypothesis test decision as the Z-test that we learned in chapter 7. So the way you would write the answer, let's see, the numbers are 81.16, 96.84, 81.16, 96.84. You literally could say the confidence interval CI equals, I can move this over actually, equals 81.16 through 96.84. That is a perfectly acceptable way of writing the confidence interval. CI, which stands for confidence interval, equals 81.16 through 96.84. So that's all I have planned for today as far as lecture stuff. So I think does anyone have any questions about confidence intervals or hypothesis tests? Okay, so I'll stop recording here, but I want to give you guys a chance to